Hi, finally we look at tan x. So if we have, f is defined as the function x mapped into tan x, and we restrict the domain to lie between minus pi over 2 and pi over 2, then we do have an inverse that exists, which is a mapping of x tan inverse x, which is x belonging to the set of real numbers. That's its domain. So we have inputs of a number x belonging to the set of real numbers. Here we have an input of an angle in radians with an output of a number. Similarly to both sine and cosine x. I forgot to write here that this is tan inverse x. Now, one thing to note is that some old textbooks might use the prefix arc. So they have arctan, arc sine, and arc cosine. But modern books, and as I've used here, use this notation: tan raised to the minus 1, sine raised to the minus 1, and cosine raised to the minus 1 to indicate the inverse. And that's just to make sure we don't mix up. So if we look at sine inverse x is not the same as 1 over sine x. As you know, 1 over sine x will give us cosec x. So completely different. Thanks for watching these videos. My name is Alistair. I'll see you on the next set of videos, which will be tomorrow. I'll post something on my channel to indicate what they are. Bye for now. Here we are again. Find the smallest angle where sine theta now is minus 0.65 and tan theta is negative. But it cannot be in the first quadrant because all are positive. Sine is positive in this quadrant, so it cannot be in this quadrant. And it cannot also be in this quadrant because we have that tan theta is negative. So the only possible quadrant it could be in is the fourth quadrant here, where cosine is positive, tan and sine are negative. So again, if we just draw a little sketch here, we'll have that it's somewhere in this, and it's a negative angle because we have that sine theta at minus 0.65 will give us, so we find the sine inverse of minus 0.65, which is approximately minus 40.5 degrees. So this angle here is minus 40.5 degrees and occurs in the fourth quadrant, and it's the smallest angle that meet these requirements. That's it for this video. Thanks, and I'll see you in the next one. Bye for now. Hi, today's videos are about inverse circular functions, and we'll start with sine x. So we have the function x, which is mapped to sine x, But if we were to map x to sine x, that will be a many one mapping. And by that I mean it would not get a unique value for each input or independent variable, and conversely you won't get a unique value for the inverse mapping back to the input. So there's no inverse mapping here if you just map x to sine x, and that's using the domain x belonging to the set of real numbers. So no inverse here, no inverse. But if we curtail our domain to the interval minus pi over 2 to pi over 2, then we can have f maps to sine x, and that's a 1 1 mapping. It has inverse sine inverse x, and that's what we're looking for. Functions must be a 1 1 mapping. Another thing to note is that for the function f, which maps x to sine x using this interval minus pi over 2 to pi over 2, the input is an angle and the output is a number. And conversely, for the inverse, we have our input is a number. So we have a input of a number. Let's just add x. So input is a number, and the output, let's write it up here, the output is an angle. Right, so input a number, and output a number for f inverse, which maps x to sine inverse x. So now we can define f to be a mapping of x to sine x with domain minus pi over 2 to pi over 2. And f inverse x as a mapping so with domain -1 between -1 and 1. As we can see above here in the graph, we've chosen to restrict our domain between minus pi over 2 to pi over 2, and in this case we have a function, we have a unique mapping of the independent variable to a dependent variable, and in the inverse, the independent variable to the dependent variable to the independent variable. So as you can see here, that's our sine x, and the inverse here, we have inputs as a number along the x axis and outputs as an angle. And for sine x, mapping of x to sine x, we have an input here of an angle with an output sine x as a number. And that wraps it up for sine x and its inverse. The next video will be cosine x, and following that will be tan x. Thanks for watching this video. My name is Alistair, and I'll see you on the next video. Bye for now. Hi, in this video we're going to be finding the associated acute angle for different values of theta. So the first is 95 degrees, and that will be in the second quadrant. A little sketch to show you like that. It'll be there. And in that quadrant we have alpha is equal to 180 minus theta, and theta is 95. That gives us 85 degrees. Next we have 3 pi over 4. A little sketch. Show that it's in this quadrant. Again, this is pi instead of 180 because we were given our theta value in radians. So that's pi take away. So alpha is equal to pi take away 3/4 of pi. That's equal to 1/4 pi. Next we have 307 degrees. That will fall in this quadrant somewhere there. Again, we're taking away from 360 degrees. We'll take away theta from 360 degrees. So alpha, because alpha add theta is 360, so alpha is equal to 360 take away 307 to give us 53 degrees. So next we have 7 pi over 3. Well, that will take us a revolution and then into this quadrant here, and what we have left is pi over 3. So that's easy to read off because we're taking away from 2 pi. So if we were to convert it to degrees, it would be 420 degrees, take away 360, which will give us pi over 3. Next we have 869 degrees. So 869 degrees, that will take away from, that's 360 times 2, which is 722 revolutions. So 869 take away 720, which will give us 149. So we're in 149 is in this quadrant somewhere. After we've completed the revolution, so R2, we end up there. And alpha will be 180 degrees minus 149 to give us 31 degrees. Hi everyone, here's another problem for us to look at. Find the smallest angle where cosine theta is equal to 0.85 and sine theta is positive. Let's have a look at our quadrant diagram. We have all of them are positive in this quadrant. So we have S, T and C, sine, tan and cosine. Then we have sine is positive in this quadrant, which is the second quadrant. The third, we have tan is positive, and in the fourth, cosine is positive. So if both cosine and sine are positive, then it can only be in the first quadrant. So our angle must be in the first quadrant. And if we do the cosine inverse of, so cosine inverse of 0.85, we get approximately 31.8 degrees, and that's somewhere in this quadrant here, the first quadrant. So this angle is 31.8 degrees. So that's the smallest angle we can get. Any other angle would be larger than that, will be negative, and so we conclude that 31.8 degrees is the smallest angle where cosine theta is equal to 0.85 and sine theta is positive. And that's it for this video. Bye for now. Here we are again. Find the smallest angle where sine theta now is minus 0.65 and tan theta is negative. But it cannot be in the first quadrant because all are positive. Sine is positive in this quadrant, so it cannot be in this quadrant. And it cannot also be in this quadrant because we have that tan theta is negative. So the only possible quadrant it could be in is the fourth quadrant here, where cosine is positive, tan and sine are negative. So again, if we just draw a little sketch here, we'll have that it's somewhere in this, and it's a negative angle because we have that sine theta at minus 0.65 will give us, so we find the sine inverse of minus 0.65, which is approximately minus 40.5 degrees. So this angle here is minus 40.5 degrees and occurs in the fourth quadrant, and it's the smallest angle that meet these requirements. That's it for this video. Thanks, and I'll see you in the next one. Bye for now.